Alright, so let's continue our discussion. We have already seen the notion of congruence modulo n, where n is some fixed positive integer. What it says is this: if a and b are two integers and n is some fixed positive integer, then we say that a is congruent to b modulo n if n divides the difference a minus b, and we express this symbolically by writing this and read it as a congruent to b, a is congruent to b modulo n, or in short as a is congruent to b mod n. Now, being a positive integer, the smallest value of n is 1. However, when n is 1, then the situation is not really very interesting, because in this case, any integer is congruent to any other integer modulo 1, or maybe to itself. And that is because 1 divides a minus b regardless of what a and b are. And that is why for any two integers a and b, we have this. So the notion is really dull when the modulus is 1, and that is why we usually assume n to be greater than 1. So greater than 1 means now the least value is 2. So let's see what congruence modulo 2, what type of relation it is. Let a and b be two integers. Then a is congruent to b mod 2 if and only if. If you do not want to write in words, you can use this for if and only if. If and only if 2 divides a minus b. Okay. Which in turn means that a minus b is even. Now, because a and b are integers, each one of them is either even or odd, and we know that the difference is even precisely when either both of them are even or both of them are odd. Why is that so? Say both a and b are even. Then a is of the form 2k1 and b is of the form 2k2 for some integers k1 and k2. In that case, a minus b is 2 times k1 minus k2. Since k1 minus k2 is again an integer, so a minus b is even. In other words, it's divisible by 2. However, if both a and b are odd, in that case they have this form. Again, for some integers k1 and k2. Keep in mind that a and b may be negative. Exactly one of them may also be negative. One of them may be 0 also, because we are not saying that they are positive, they are just some integers, but now they are both odd. Now what happens to a minus b? If you calculate using these expressions, 1 and minus 1, they cancel out, and you again get this. So again this is divisible by 2, and that is why you can write like this: if and only if both a and b are even or both are odd. Okay, so this is just one simple observation about this relation when the modulus is 2. But let us now go to a general discussion. What now we are going to do, we will consider a general modulus n which may be 2, may not be 2, but we will also take any integer. Let a be an integer. A may be positive, may be negative, A may even be 0. But we know whatever it is by the division algorithm. There exist unique integers Q and R such that two things, you know from division algorithms. So here what we are doing is that we are dividing A by N, and our quotient will be Q and remainder will be R. That means you get this equation Qn plus R, and you also get these inequalities. You know that remainder is a non-negative integer, and also it's less than the divisor, provided the divisor is positive. If this divisor is, if there is a possibility that the divisor may be negative, here you do not write simply the divisor, but its absolute value. But for us, n is positive, so we can write like this. Then A minus R is equal to Qn, and so n divides A minus R because Q is an integer. Note that this equation by itself is not enough to conclude this. You also need the divisor to be non-zero. Never forget this, okay? When you conclude a divisibility relation from an equation like this, make sure that the divisor is non-zero. Because for us n is positive, so that means it's non-zero. So we have this. But this implies that A is congruent to R mod n. Okay, but what's the big deal about this? See, the thing here is that A is an integer, any integer. However, we have found that any integer is congruent to R modulo n. Now, there are of course infinitely many possibilities for A. However, R has only finitely many possibilities due to these inequalities. Since R is one of the numbers zero, 1, 2, and so on up to n minus 1, we see that A is congruent to one of these numbers. That means as far as the modulus n is concerned, although there are infinitely many integers A, but when we calculate this relation, what A is congruent to, A will be congruent to infinitely many numbers. But among them, these special numbers are there, which are only finite in number. And A will be congruent to one of them. And that too, exactly one of them. That is also important to note. Why? Because R is unique? Well, truly speaking, simply the uniqueness of R does not guarantee that A is congruent to exactly one of them and not the others. We will need something else also. But you can understand that we have reduced the scope drastically. This is a very significant simplification. When talking about congruence, on this side you can have infinitely many integers, but on this side you can always consider one of these, and that's enough. So as far as congruence modulo n is concerned, actually these numbers are enough. In a sense, we see that A is congruent modulo n to one of these n numbers. Okay, so that is one observation that we see, which is a consequence of the division algorithm. In particular, A is congruent to 0 mod n if and only if n divides A. Well, why? Well, you apply the definition. A is congruent to 0 mod n if and only if n divides A minus 0. If and only if n divides A, that is why. And these numbers have a name. The numbers form the set of smallest non-negative residues modulo n. Now this word residue means that something has happened and a kind of process has happened. Now it's over and something is there, something is left out as a byproduct of that process. So that something can be thought of as division by n. So when you divide something by n, what are you trying to do actually? In a sense, you are looking at multiples of n, and your aim is to look at multiples of n and go as close to the given number as possible. Of course, you may not be able to hit the number precisely. That will happen only when A is divisible by n. Otherwise, you will just either exceed the number or you will fall short of reaching the number. So in that process, there is a leftover. That is your residue. And these are the smallest non-negative residues. Non-negative, of course, because these are all non-negative. And smallest. Okay, smallest non-negative residue. Or in other words, they are said to form the set of smallest non-negative residues modulo n. Don't forget to mention this modulo n. Otherwise, if you do not mention this, it should be understood that in the background there is a modulus, and that is fixed. These residues are important, being smallest and non-negative, but there is a generalization of this notion. in general, a collection of any n integers a1, a2 and so on, an is said to form a complete set of residues modulo n, or a complete system of residues modulo n if each integer means you take any integer, okay, if each integer is congruent mod n. I quit writing modulo n every time. I will simply write mod n, okay, briefly. If each integer is congruent mod n to exactly one of these numbers, 1, ak. If a set of numbers has this property, then that set is said to form, or simply that set is called a complete set of residues modulo n, or a complete system of residues modulo n. Now, our previous discussion has shown that these numbers form a set of residues modulo n, in the sense that every integer a is congruent to one of them modulo n. However, we did not really address how it is that every integer is congruent to exactly one of these numbers modulo n. Okay, we are not going to answer that right now, because we will need some properties of this congruence modulo n. Then only we will be able to answer this more efficiently. I mean, we can struggle with this right now, but we will be doing many things which at this moment will be counterproductive. Let us just go with the flow for now, and then when we have gathered enough material, enough results, then we will come back to this. Okay. Let us first get a feel for these things. So let us now see an example of a complete set of residues modulo n for some specific n, and n is 7 here. I can continue from here itself. For instance, the numbers, so these are some numbers, -12, -4, 11, 13, 22, and then two more, 82 and 91, form a complete set of residues modulo 7. Well, we can observe this thing about these numbers. Minus 12 is congruent to 2 mod 7. Then minus 4 is congruent to 3 mod 7. Eleven will be congruent to 4 mod 7. Then 13 is congruent to 6 mod 7. 22 is congruent to 1 mod 7. 82. What is the multiple of 5, I think, mod 7. Let me just see. 7, yes, 77. 82 minus 5 is 77. And there is one more, 91, right? Which I think is divisible by 7. 7 times 1 is 7, 21, and 3 times 7 is 20. Yes. And 91 is congruent to 0 mod 7. How do these congruences tell us that this is a complete set of residues modulo 7? See, this is how it works. To show that it's a complete set of residues mod 7, what is it that you have to show? You take any integer and show that that integer is congruent to exactly one of these numbers modulo 7. So let me take any integer. Let a be any integer. Now from our previous discussion, we know that a is congruent to R mod 7 for some R in this set. This we get from the division algorithm. Now, do we get all the R's here? Let us see. 0, 1, 2, 3, 4, 5 and 6. Yes. And that is why, because R is coming from this set and R will be appearing here somewhere, so that is why A is congruent to one of the above numbers mod 7. What is the justification? The justification goes like this. A is congruent to R and R is congruent to one of these, depending on what R is. One of these numbers mod 7. So A should be congruent to one of the numbers mod 7. But why? That's because this relation congruence modulo n is an equivalence relation, and that's why it is reflexive, symmetric, transitive, all those things. That's why I was saying a moment ago that at this very moment we cannot justify everything. We have to wait for the results to develop, and then only we can properly justify these things. But at least you can see why this is happening and why these numbers will form a complete set of residues modulo 7. There is still that question we haven't answered, namely, how do I know that this A while being congruent to one of these numbers mod 7 is also not simultaneously congruent to some other number mod 7, because the definition of complete set of residues demands that each integer be congruent to exactly one of the members mod 7. That exactly one part still we have left hanging. Okay, so let us take it for granted for now that this happens. We will see the reason soon, but let's then move on. One other observation is this. An observation of some importance is that if in a set of n integers no two distinct elements are congruent to each other mod n, then they form a complete set of residues modulo n. Then they form a complete set of residues mod n. Oh, I actually totally forgot about another thing that I should have said before taking that example, and it is that although I did not mention it generally, but here I showed the reason why that set of numbers is a complete set of residues mod 7. That is, I used these numbers. So that general observation is just about that. Okay, so there I did not miss anything in fact. Alright, so let us now see some properties. So let's now start proving things. The first result tells us precisely when two integers are congruent to each other modulo n in terms of remainders that they leave when divided by n. And this is Theorem 4.1. Let A and B be two integers and n be a positive integer. See, there everything in mathematics now has to be understood in some context. Actually, if you look at this inequality, it does not say that n is an integer. It simply says that n is a real number that is at least 1. But because in the context of number theory and in some other places, n usually denotes an integer. So we won't be every time writing and n is a positive integer. When you see things like this, you assume that n is an integer, and because of this n is a positive integer if something otherwise is not stated. Then A is congruent to B mod n if and only if A and B leave the same remainder when divided by n. Let us now prove this. It's a very easy result. First, let A be congruent to B mod n. Now, by the division algorithm, there exist unique integers Q1, R1, Q2 and R2 such that A is equal to Q1n plus R1, B is equal to Q2n plus R2, R1 is non-negative and less than n, and R2 is also non-negative and less than n. So we are getting these things from the division algorithm. Loosely speaking, we have divided A and B both by n, and we have got quotient Q1 and Q2 and respective remainders R1 and R2. All right. Then you can calculate A minus B. A minus B will be what? Q1n plus R1 minus Q2n plus R2. Okay, and this can be rearranged. To write like this: Q1 minus Q2 times n plus R1 minus R2, or you can further rearrange things and get this: A minus B minus R1 minus R2 is equal to Q1 minus Q2 times n. Hence, n divides this difference. Okay. So, A minus B is congruent to R1 minus R2 mod n by the definition of congruence. All right. However, okay. Yeah, instead, let me just change this a little bit. Instead of writing these things, I stop here and note what is given. It is given that A is congruent to B mod n. Since A is congruent to B mod n divides A minus B. Okay. Now because n is dividing A minus B, and from here we get that n divides A minus B minus R1 minus R2, we get this. Actually I should have kept that line that n divides this, but anyway you understand. Hence n divides A minus B using properties of divisibility that we have already seen in previous chapters, minus this minus R1 minus R2, or n divides R1 minus R2. Alright. Now, before considering A minus B, we could have made one assumption without losing generality, namely that R2 is less than or equal to R1. We can make it now also. Suppose R2 is less than or equal to R1. There is another similar case where R2 is greater than R1. In that case, you just consider R2 minus R1. But how? You cannot just simply out of the blue consider something without any reason. Because n divides R1 minus R2, n divides its negative also, which is R2 minus R1. So if R2 happens to be greater than R1, you consider that case. But let us now see what we get in this case. Then, okay, now watch this. We are going to use these inequalities. First of all, 0 is less than or equal to R1 minus R2. Why? Because R2 is less than or equal to R1. So from this inequality itself you are getting this. However, note also that R2 is greater than or equal to 0. So subtracting R2 means subtracting something positive from R1 or subtracting 0. If R2 is 0, R1 stays R1. Otherwise it decreases. And that is why this is less than or equal to R1 itself. And this second inequality comes from the non-negativity of R2. However, we are also given that R1 is less than n. Okay, now you look at these inequalities and this divisibility relation. This relation says that R1 minus R2 is a multiple of n. These inequalities say that R1 minus R2 is non-negative but less than n. Now, let's imagine the non-negative multiples of n. The first multiple is 0, then n, 2n, 3n, and so on. This can be none of those positive multiples. So that means it has to be equal to 0, and that's because this is strictly less than n, so it's also less than 2n, 3n, and the other multiples. So the only possibility is that this has to be equal to 0. So we must have, if you want, you can write these things in words. Okay, I am not going to do that. I mean, I am saying orally, but I am not going to write. I am simply going to write, thus, we must have R1 minus R2 equal to 0. In that other case, if you are having R2 greater than R1, You just consider R2 minus R1 and have considered similar inequalities. That is, R1 is equal to R2. But this is what we wanted to prove, right? Assuming that A is congruent to B mod n, we wanted to show that A and B leave the same remainder when divided by n. But there is that converse part also. Conversely, let A and B leave the same remainder when divided by n. Then there exist integers q1, q2 and r. This time there is only one remainder. Actually there are two, but they are the same. So we are simply taking r such that A is equal to q1n plus r, B is equal to q2n plus r, and r is non-negative and less than n. Here actually in this part, converse part, these inequalities will not really play any role. We concentrate on the equations. Now, what is A minus B? Without writing too much, you understand that r and minus r will cancel out. And after taking n common out, you are getting q1 minus q2 times n. So this converse part is a bit easier. You can now almost see what to write next. Hence, n divides A minus B, and so A is congruent to B mod n. Now this result roughly says this, that congruence is a kind of equality only. If you divide by a modulus in two integers and they leave the same remainder, then we are considering them to be equal. It's not literal equality, but it is equality in some sense. In fact, it's an equivalence relation also. If you are unfamiliar with this term equivalence relation, don't bother, okay, right now. Okay, let us now see an example that illustrates this thing. In this example, we are going to see both the ways. Consider what are the numbers? Minus 56 and minus 11. The thing we are going to note about these numbers are these. Note that minus 56 is equal to minus 7 times 9 plus 7. Do not keep the numerical equations like this, okay? I mean, simply you just do not pay any attention. Please verify these things. It's not that you have to do them by hand. You can use calculator. At least see that these are correct. And minus 11 is equal to, so that means this will be minus 2 times 9 plus 7. You can see that when you divide minus 56 by 9, the quotient is minus 7 and remainder is 7. How do you know that you have got the correct equation? That's because that other number is non-negative. In fact, it's positive and less than 9. And you know from the division algorithm that when you divide an integer by something, there is only one quotient and one remainder. So simultaneously you won't get another equation giving you the same kind of things, I mean numbers having same property. Similarly here also, dividing minus 11 by 9, we have got the remainder 7, which is a legitimate remainder, and that is why this is also a legitimate equation, the kind of equation we are considering here. Because minus 56 and minus 11 have left the same remainder when divided by 9, that's why they must be congruent to each other modulo 9 by the above theorem. Hence, I mean, one can of course verify this using the definition, but we are illustrating that theorem, right? So we can view at it like this also. Going in the other direction, we have this. Since minus 31 is congruent to 11 mod 7, minus 31 and 11 leave the same remainder when divided by 7. And in fact, these are the equations for those divisions. Minus 31 is equal to minus 35 plus 4, right? Minus 5 times 7 plus 4 and 11. 11 is simply 1 times 7 plus 4. So yes, they are leaving the same remainder, 4. I am very bad at numerical calculations orally. I cannot do anything mentally. I mean, it is so bad that I am worse than almost everyone. But I was at a university doing something, kind of a teaching job. Nothing big, something small. There I used to teach number theory. In fact, this very book in a course. There I came across one individual, one boy, who was exceptional in numerical calculation. I mean, he could, I think he could multiply to a 4-digit number and a 5-digit number at lightning speed. Okay, so such people also exist, and I was astonished in one of the classes that I was writing some numbers, and he just instantly told me what I should write. And in fact, he also told me that there is a mistake somewhere in what I wrote in a large integer. Okay, so I just suddenly remembered that. Alright. So after this comes the many properties of this relation, congruence modulo n. The previous result is something, but it's not really the heart of everything. The main results are coming next, some of which may seem like somewhat dull, but individually they may not seem like much, but together they will be very powerful, you will see. So let's just see the theorem. As good as that boy is, I am as bad. I can understand things, but very slowly, and my mental calculation is even slower. I cannot, in fact, do unless I am writing things down. Let n be greater than 1. That means n is a positive integer. And let a, b, c and d be any integers. There are some parts to this theorem. Part A. A is congruent to A modulo. In the first three parts, in fact, collectively will show what I was saying, that this congruence modulo n is an equivalence relation. But again, I am saying that if you do not know this term, just don't bother. So I should have written if. If A is congruent to B mod n, then B is congruent to A mod n. Do not be afraid by the length of this theorem, okay, I mean the length of the statement. These individual statements are not really very difficult to prove. They are 1 or 2 line proofs. Next comes transitivity. If A is congruent to B modulo n and B is congruent to C modulo n, then A is congruent to C modulo n. Then we have some algebra involving congruences. You can add 2 congruences. If A is congruent to B mod n and C is congruent to D mod n, then A plus C is congruent to B plus D mod n. And you can also multiply congruences as if they are equations. AC is congruent to BD mod n. Further, you can add and multiply the same term on both sides of a congruence. E. If A is congruent to B mod n, then A plus C is congruent to B plus C mod n and AC is congruent to BC mod n. And lastly, this one is in fact the one which is the most powerful according to me, if A is congruent to B mod n, then A to the power k is congruent to B to the power k mod n for any positive integer k. Okay, so I somehow managed, I did not run out of space. Now we will prove these things one by one. So the first one we have to prove is that any integer is congruent to itself mod n, and this is almost immediate. And the reason is this. So we start our proof from here. And in this proof, I won't really be writing everything formally. I will just show you the main thing. What do we need to do to prove that A is congruent to A mod n? We need to show that n divides A minus A. But A minus A is 0, which is always divisible by any non-zero integer, since n divides A minus A equal to 0, actually we should not write like this, but people do write for the sake of brevity. N divides A minus A equal to 0. This is not how we should write. We should write like this: n divides 0, and so n divides A minus A. But you get the point. Okay. So that is why A is congruent to A mod n. So that means we have proved part A. Next comes part B. If A is congruent to B mod n, then B is congruent to A mod n. Since A is congruent to B mod n, n divides A minus B. But then n divides B minus A as well. Why? Because when n divides an integer, it also divides its negative. So B is congruent to A mod n, and that is part B. Next comes part C. Because A is congruent to B mod n and B is congruent to C mod n, so we have n dividing A minus B and n dividing B minus C. So now you understand that I won't be writing everything formally. But then by properties of divisibility, n will divide the sum of these two numbers as well. That is, let me at least write so. So n divides A minus B plus B minus C. Or, because minus B and plus B cancel out, and we are left with A minus C. So A is congruent to C mod n. Okay. Next comes these numerical, algebraic operations, addition and multiplication. A is congruent to B mod n and C is congruent to D mod n. It's a little bit different from this, okay, do not get confused. So this is D. That means we are getting this divisibility because A is congruent to B mod n, and we also simultaneously get this. Alright. This means, again, just like that one, let's add them up. And we get this, or rearranging the things a little bit, we get A plus C minus of B plus D. So A plus C is congruent to B plus D mod N. Now, in order to get the product part, we won't really be working only with the divisibility relations. We need equations. You see, because n divides A minus B, so A minus B is equal to n k1 for some integer k1, or A is equal to n k1 plus B. Similarly, from this one we get C minus D equal to n k2 for some integer k2, and from that we get C equal to n k2 plus D. Now we multiply these two equations, ordinary multiplication of equations, and that gives us AC equal to n k1 plus B times n k2 plus D. Now if you multiply the terms out, let's see what we get. First we get n square k1 k2, okay, n square k1 k2. Then we also get n k1 d plus dn k2, and finally d. Now you look at that expression, and on this side you look at AC. So we are getting AC minus BD equal to, so we are taking BD on this side, and we will be left with this on the right side, where you notice that every term has n in it, and that's why n can be taken as a common term outside. And inside we will be having n k1 k2 plus k1d plus bk2. It does not really matter what we have within the parenthesis. What matters is that this is, after all, an integer. So n divides AC minus BD, or AC is congruent to BD mod n. So that's how we have the product of two congruences as well. In part E, we have, this is given to us, okay, and n is, C is any integer. From this we get n dividing A minus B. So n also divides A plus C minus of B plus C, because if you look at it, C and minus C will cancel out and we will have only A minus B. So this is in fact the same as A minus B, and that is why A plus C is congruent to B plus C mod n. But there is a product part in this one also. For that, from this divisibility relation, you get this as well. If n is dividing A minus B, then n would divide some multiple of A minus B as well, this multiple, or n dividing AC minus BC. So AC is congruent to BC mod n. All right, and finally we have that power, that statement. That statement we have to prove by induction. It can be proved using binomial theorem also, but we won't do that here. Part F. So here we are given this and we need to prove this for any positive integer k. Note that we do not actually have to do anything for the basis of induction, which is the case when k is equal to 1, because in that case this congruence just reduces to what is already given. So that is the basis for our induction. Now, as induction hypothesis, let this statement be true for some k greater than or equal to 1, some positive integer k. We now have to prove that a to the power k plus 1 is also congruent to b to the power k plus 1. Okay. That means we need to prove that n divides their difference. So let's take their difference and see what we can do with the difference. What we are going to do here is we will introduce middle terms. This is often called middleman's trick in maths. We subtract a to the power kb, but to balance it out, we also add it, minus b to the power k plus 1. Now, if we take a to the power k common out from the first two terms, we then get a minus b. And here we can take b common out. Okay. From this, we know that n divides a minus b. And from the induction hypothesis, we know that n divides this as well. So from properties of divisibility, we know that n divides this. i.e. n divides this. So we have our induction step. Do not be fooled by the casual nature of this discussion, okay? While you are writing something on paper or you are, say, typing a solution out in some kind of software, write everything formally, okay? And this, no one can teach you this. You have to get it on your own through practice. I mean, every now and then we show how to write, but it's an art. You have to get it on your own. So that completes the induction, and this also completes the proof of this result. Now, before I end the video, let's see two examples in which we will be using these things to prove non-trivial divisibility statements. And the first example is this. And in these examples, we immediately realize how powerful this idea and these results are. Suppose you want to show that 41 divides 2 to the power 20 minus 1. Now, of course, 2 is not a very big number, but multiplying 2 copies of 20 will really be large. although not unimaginably large, but still large. And this kind of questions can be answered very nicely using these properties of congruence. What we have to do in such situations is we start with a congruence, some convenient congruence. The author has noticed that we have this minus 9 mod 41. Why though? This is just 32, and the difference between 32 and minus 9 is 32 plus 9, which is actually 41, and 41 is divisible by 41, so we have this congruence. Then by applying part f, which we have proved just now, we can raise both the sides to the fourth power. Okay, so that this becomes just 2 to the power 20, whereas this one is minus 9 square times minus 9 square, or 81 times 81 mod 41. Now the nice thing here is that you do not even have to multiply these two things and then do all the calculations. If you look at this, if you notice this congruence, 81 minus minus 1 is 82, and 82 is divisible by 41, and that's why you have this nice congruence. So by the fact that you can multiply two congruences, in this case both the congruences are the same, using that fact you get this. And this implies that 81 times 81 is congruent to 1 mod 41. Now 2 to the power 20 is congruent to this mod 41, and this is congruent to 1 mod 41. So applying part C of the just proved result, namely that congruence modulo n is transitive, we get this. And that is why 41 divides this. Okay, so without calculating the actual number and then seeing by actual division whether 41 divides this or not, using the theory of congruences, we have been able to do it almost without any effort. Admittedly, these values must have been cherry-picked to show how efficient this congruence theory is. But in general also, you will see, you will be amazed at how many situations arise in which congruences and their theory save you from unimaginably large calculations. And next comes one more. And this one is really, really large. I mean, if someone adamantly doesn't want to use congruences, then it's next to impossible. Find the remainder when this number is divided by 12, 1 factorial plus 2 factorial plus 3 factorial and so on up to 100 factorial is divided by 12. Forget about adding these numbers. 100 factorial is the product of the 100 natural numbers, and that itself will be extremely large. But anyway, how can we find the remainder using congruences? Because it's given as a kind of task, let me write a solution. You see, the observation here is this. Note that four factorial is 24, and 24 of course is congruent to 0 mod 12, because 24 is divisible by 12. So for any integer k greater than or equal to 4, k factorial, you notice one more thing, that it's customary to write things like this. I mean, write a statement, one part of which is an ordinary equation and one part is a congruence. You can do that, okay. There is no chance of confusion, but provided you know what you are writing. Now, when you take k factorial, where k is at least 4, this becomes 4 factorial times 5 times 6 and so on up to k. Now, because 4 factorial is congruent to 0 mod 12, so this is also congruent to 0 mod 12. But the question is, which part of the previous result have we used here? It is that result. You see, on both sides of this congruence, you can multiply by an integer, say c. If a is congruent to b mod n, then ac is congruent to bc mod n. That c is this one here, 5 times 6 times up to k. Okay, so using that part, we are getting this. Hence, using the fact that you can add congruences next, we get this. Hence, 1 factorial plus 2 factorial plus 3 factorial. Let me write a couple more. Is congruent to 1 factor. Let me just write 1 itself, okay, because any integer is congruent to itself, plus 2 factorial is 2, 3 factorial is 6, and then all these other factorials are congruent to 0 mod 12. So their sum is congruent to this sum. Because 9 is non-negative and less than 12, so that means 9 is the remainder. Hence, the required remainder is 9. Do you see how easily this has come out? And the absence of congruence is, you cannot even imagine. Who would want to calculate this, even using computer? It's unnecessary. So let me just stop the video here itself. There are some other things in this section to consider about congruences. One is that, you see, in an ordinary algebraic equation, we can cancel the same term from both sides if it is multiplied and is non-zero. Like if you have AC equal to BC and C is non-zero, then you can cancel C from both sides and write A equal to B. Can you do the same thing in a congruence? Well, not always, but in a special case. So we will see those things. Okay. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer from a mathematical room. Have a nice day.